Hello everyone. Welcome to the week 0 for fluid mechanics course on NPTEL, bearing the code CE85. I am Shubhranshu Purkasta and I am currently working as a research scholar via lateral entry PMRF in the Department of Civil Engineering at IIT Kharagpur. My research area is computational fluid dynamics. To begin with, what is mechanics? Mechanics deals with the relationships between force, matter, and motion among physical objects. Now, there are two aspects of mechanics. One part is statics, which deals with objects in rest, whereas the other part is dynamics, which deals with the forces responsible for objects in motion. In fluid mechanics, we specifically study about fluids, whether they are in rest or in motion. The prerequisites for learning fluid mechanics include engineering mathematics. We should have a very good conception related to vector calculus and differential equations. And by differential equations, we mean both ordinary differential equations and partial differential equations. The reason being that most of the physical processes in nature can be replicated mathematically by means of differential equations. Now, if it is a one-dimensional process, then we go for ordinary differential equation, and for multi-dimensional uh, situations, we go for partial differential equations. Then you should have firm idea of engineering mechanics, which includes Newton's laws of motion. Then the various branches of mechanics like kinematics and kinetics. Now, kinematics deals with the motion of the object without considering the background forces, whereas kinetics deals with statics and dynamics, that is, the forces which are responsible uh, when the bodies are in rest or are in motion. Now, we all know very well that there are three states of matter: solids, liquids, and gases. Now, in solids, the intermolecular forces of attraction is very strong, and in liquids and gases it's relatively much lesser in comparison to that of solids. Now, liquids and gases constitute fluids, but rather than looking at the atomic level, if we look uh, at the fluid and the solid from the engineering point of view, then a fluid is a substance that uh, deform continuously under the action of shear, means it cannot resist shear force. Now, this particular figure shows a solid. Now, if we apply a shear force, then there will be a shear deformation. But the moment we remove the force, the body will come back to its original position. So basically, Hooke's law is valid for a solid body. However, if you consider a similar situation in case of a fluid, then once we apply a shear force tau, what happens? The fluid deforms continuously. Even if we remove this tau, if this shear stress tau is removed, even then the fluid will not come back to its original position and it will deform continuously, and that's why Hooke's law is not applicable for fluid, but rather laws like Newton's law of viscosity, where shear stress is directly proportional to the rate of strain, is applicable in case of fluids. Now, details of Newton's laws of viscosity and what is the exact definition of the uh, engineering definition of a fluid, all these things are discussed in this course. So once you will go through the lectures available in the portal, the NPTEL portal, you will definitely understand in a much better way what is the definition of a fluid and how it is different from a solid. But as a week 0 run, this is just a preliminary idea on what is a solid and what is a fluid. Then uh, I have taken a problem. In the problem, there is a cross section of a river which is approximated as a trapezoid, having a base width of 200 meter, and the width of the water at the top is 250 meter, and the side slope is 1 is to 2, 1 particle is to 2 horizontal. And for a flow velocity of 2 meter per second, we need to estimate the discharge in meter cube per second. So, in order to solve this problem, you need to have an idea of what exactly is discharge. Now, from common sense, discharge is defined as the volume flow rate, that is the volume of water flowing through this particular cross section per unit time. So discharge can be defined as volume of water flowing, that is V, by time t. Now volume can be written as area A into length L dimensionally divided by time. Now L by T, the dimension of L by T is basically velocity. So A into U. So discharge becomes area into velocity. However, there are more basic approaches to arrive at this relationship. But at this stage, as the course lectures, you have not started with the course lecture. Uh, we are just dealing with the very basic definition of discharge. Now, what is the area of a trapezium? The area of a trapezium is half into height, that is the distance between the top width and the bottom width of this channel is the height into the summation of the top width and the bottom width. So here the top width say is B1, which is 250 meter, and the bottom width is say B2, which is 200 meter, and the side slope is 1 vertical is to 2 horizontal. Let's the side slope in general is n1 vertical is to n2 horizontal. Then the height is given by n1 into b1 minus b2 by twice n2. Now this we can very easily derive by using some simple trigonometric calculations. So once you have the height, you already know the value of b1 and b2, which is 200 meter and 250 meter. You put the value of height and b1 b2 in this equation, you will be getting the value of area, that is A, and the value of u is 2 meter per second, which is already given in the question. You can very easily calculate the discharge in meter cube per second. Second problem is, what is Reynolds number for a pipe of diameter d? Now Reynolds number is defined as the ratio of the inertial force to the viscous force. Now what is inertial force? Inertial force is the force that we obtain from the Newton's second law of motion, and the final form of this force is mass into acceleration, that is m into a. Now from the definition of density, mass can be written as density into volume, and acceleration is velocity by time. Now dimensionally, volume is nothing but area into some length dimension. So density into area into length dimension into u by t. So this is the dimensional form of the inertial force. Now what is viscous force? Now viscous force can be directly written as can be directly taken from the Newton's law of viscosity, the mathematical form of the Newton's law of viscosity, where tau is the shear stress, mu is the coefficient of dynamic viscosity, and du by dy is the rate of shear strain or the velocity gradient. Now how we arrive at this Newton's law, what are the physical implications of Newton's law, everything is discussed in the week one of this lecture on fluid mechanics. But for the time being, we are not discussing that. We are simply assuming that there is something called Newton's first law of viscosity. Now if tau is shear stress, then stress is force by area, then simply writing the dimensional form of this equation, we can write viscous force is equal to area into mu into du is basically u by L. Now simply putting these expressions, the dimensional form of these expressions for inertial force and viscous force in the equation of Reynolds number, we get that Reynolds number is equal to rho LL by T mu. Now the dimension of L by T is nothing but velocity, so rho UL by mu. Now you have to keep one particular thing in mind, that this L is the characteristic length. Now in case of a pipe of diameter d, the characteristic length is d, so this L will get replaced by d. So this is basically Reynolds number. So like this we have many other dimensionless numbers which are very important in fluid mechanics. So this particular course on fluid mechanics is a very basic course which starts with the definition of fluids, the basic properties of the fluids, then it deals with hydrostatics, that is the behavior of the fluids at rest. Then gradually uh, the lectures migrate towards the kinematics of the fluids, where we learn about the velocity field and the acceleration field. Then finally we go with the energy conservation, the continuity equation. Now the mechanics, whether we study solid mechanics or fluid mechanics, there are some conservation laws which are valid for both solids and fluids. However, the variation in the final form depends on the constitutive properties of the solids and fluids. So uh, those basic conservation laws include conservation of mass, conservation of linear momentum, conservation of angular momentum, and conservation of energy. Now conservation of mass uh, give rise to continuity equation for fluids. Then conservation of momentum gave rise to Navier-Stokes equation. Similarly, we have conservation of angular momentum and we have conservation of energy. Now, conservation of energy for a steady incompressible fluid give rise to Bernoulli's equation. So, all these things are discussed, and finally, uh, there are some approximations, means where you can find the exact solution of Navier-Stokes equation is also discussed here. So, all the best and hope the students will enjoy this course. Thank you.